Welcome back, everybody, to this afternoon's session. Hopefully you had a chance to network and to talk to some of the startups, through to the Eli Harari, through to some of the speakers from this morning's session. So welcome to this afternoon's session. Hopefully there's no new people here, but if there is anyone new, today is very much around day one of the showcase, very much around the academic pipeline. So again, theme of today is very much around industry-led, academic-fed. And this morning we had a range of speakers talking around some of the opportunities, not just on graphene, but of the whole family of 2D materials. And one of my take was some of the combinations of the 2D materials, 2 plus 2 to make 6 in my language, that by combining these 2D materials, you can start to make some discrimination, some difference in your products and applications. So we're going to continue the theme this afternoon. We've got a number of other speakers who are going to continue. And then later on this afternoon, for those who can stay, at the end of the day, we're going to sort of transition to our Brit and Eli Harari Graphene Prize this evening. And for those who can stay, we've brought the sun, hopefully, for a barbecue this evening in Manchester weather. So the good news is we can hopefully grab the barbecue outside and eat inside if it's raining, or stay outside if the sun comes out. So with that, a few people have started to come in, and I think the noise is starting to die down next door. So delight to introduce our next speaker, Dr. Marcelo Lozada Hidalgo, who's going to talk about two-dimensional proton conductive materials. Yeah. Marcelo.
Thank you. Can you hear me? Yeah, good. Thank you, James, for the introduction. Today I would like to talk to you about our work investigating 2D crystals as proton-conducting materials, and specifically how you could use them for hydrogen and energy renewable technologies. So, as you probably know by now, there's a large group of materials like graphite, HBN, MOS2 that consists of layers stacked on top of each other. And key to this is that the bonding between these layers is weak, so we can isolate one of these layers to form a 2D crystal. Now, early on, it was shown that these crystals are impermeable to all atoms at ambient conditions. Not even helium, the smallest of atoms, can permeate. And this was demonstrated in a now series of seminal experiments by Bunch et al., also Andre Geim in Manchester. Basically, what you do is you drill a cavity in a substrate, and you seal your cavity with a two-dimensional crystal. It could be graphene, HBN, whatever you want. And then you pressurize this cavity, and what that does is makes this 2D crystal to bulge upwards, pretty much like a balloon. And what you can do is measure the deflection of this balloon with an atomic force microscope, and from this deflection, you can infer the pressure inside the cavity. And it is doing these experiments that it was shown that these crystals are impermeable to all atoms at ambient conditions. So in this context, back in the day, almost 10 years ago now, we decided to ask the question, well, are these crystals impermeable to absolutely everything? And the smallest thing that you can manipulate at ambient conditions is the proton, the nuclei of hydrogen. Not the solvated proton, but the actual nuclei of hydrogen. So to do this, what we did is we did the following experiment. We drilled a hole in a substrate, usually silicon nitride. This hole is typically a couple micron in diameter. And then you sandwich this, and then you suspend a 2D crystal over this hole. So you have like a fully suspended 2D memory. It could be graphene, MOS2, HBN, anything you want. And then you sandwich this suspended 2D crystal between 2 layers of proton-conducting polymers, usually naphthalene, and 2 layers of proton-injecting electrodes. So what you do is apply a bias in this device. Protons are injected into the polymer. The protons may or may not cross through your crystal. And then you close the circuit in the same way. So by measuring the resistance of these devices, you measure the proton transmission through your 2D crystal. So basically what you see is something like this. This is current versus voltage for different crystals. In red, we have one crystal known HBN, hexagonal boron nitride. In blue, we have graphene. And in green, you have monolayer MOS2. And what we find is that all these crystals display very different permeabilities. Importantly, very recently, this was just like last year, we mapped with nanoscale resolution the proton transmission through this crystal. So this is our suspended membrane. This we can measure with basically a pipette, very small pipette, nanoscale resolution, and we measure the proton transmission through the crystal. And this was important because when we discovered this, there were questions, well, are these crystals intrinsically permeable, or is it that you have some defects in your material? What we show is that these crystals are intrinsically permeable to two-dimensional crystals, to protons. Key to this is we also see an extremely sharp dependence on the number of layers. So if you measure one layer of graphene or one to up to 3 layers of hexagonal boron nitride, we see proton permeation. But if you put 2 layers of graphene or 4 layers of HBN, we don't see any permeability at all. So it's an extremely sharp. It depends really on the number of atoms in these membranes. Monolayer MOS2, as you see, is impermeable to protons. Even just a single layer of MOS2 is impermeable. So to rationalize these results, what we said, well, these protons are piercing the perfect crystal. And to do so, they need to go through the electronic cloud in the material. So what we have here is a DFT calculation of the electron cloud density in these crystals. In this calculation, the darker it looks, the more dense the electronic cloud. So as you see, HBN, which was the most proton permeable of all the crystals we studied, is the one that is most translucent. So its electronic cloud is more porous. This is followed by graphene. And for MOS2, for which we didn't see any permeation, you have very dense electronic cloud. So the electronic cloud porosity is very low. Now, to explain the layer dependence, it's also straightforward. We found that remember we saw proton permeation for up to 3 layers of HBN. This is because this crystal stacks in a pattern known as AA prime. So that means that all the atoms in each layer are stacked directly on top of each other. That means the space in the hexagonal ring, so this space here, remains open even for multiple layers. However, for graphene, we have something called AB stacking, and this means that the atom from the next layer sits directly at the center of the hexagonal ring of the previous layer. And because of that, you block this pore for permeation. This is why you don't see permeation for 2 layers of graphene. So this was early results, and we've been doing various lines of research, and today I would like to show to you 2 of our latest and I think most promising research directions. One of them is, well, we have a 2D crystal that is permeable to protons, and because it's very thin, you should be able to concentrate very intense electric fields in it. So we want to study what is the role of electric fields in these crystals and how we could use it in energy technologies. So the motivation for this is, you probably know, this is a bit technical, but bear with me for a minute, is if you have a classical electrolyte interface, so any electrochemical system you can think of, you have an electrode, this is usually a metal, and an electrolyte. So when you apply a voltage, the charge density in your electrode and the electric field are related fundamentally. You can change you can change, for example, the solvent. This will change the electric constant. This will modify the electric field. You can change the pH. This will change the surface density, the charge density in your electrode. You can change electrolyte concentration. This will change the pi length. But at the end of the day, once these parameters are fixed, the charge density and the electric field are fundamentally linked, and there's just no way around that. However, in 2D crystals, it's now very well established. You can decouple these parameters using that technique known as double gating. And people have been using it to basically modify the band structure of these materials for quite a long time. You could use crystalline dielectrics, and people play with different quantum phases into the crystals. You probably heard some of these talks in these sessions. You can also use electrolytes as a gate. And when you do that, what you can do is, for example, quench the band gaps into the semiconductor. So you could turn a 2D semiconductor into a metal, for example. But the point is, with this technology, you can decouple the electric field and the charge density in your electrode. And why do we care about this? Well, so to see why we care about this, I want to focus on 2 of the simplest processes you could have in an electrochemical interface. One is the transmission of a proton, which we've been discussing. The other one is the adsorption of a proton, so chemisorption. And this, basically, the way you can monitor in graphene is, if you measure the so this is graphene, you have 2 electrodes, and you measure the in-plane electronic current. When protons adsorb, they act as scatterers, and this triggers something called as a conductor-insulator transition. So graphene becomes an insulating material. So basically, this is what you see in this here, in this transition here. This is the electronic conductivity, so you measure in-plane electron transport through graphene. And as you apply a gate voltage, what you see is a sharp transition to insulator. And this means your system has become protonated, hydrogenated. So there's a lot of hydrogen adsorption on this system. So why do we want to study this with a double-gated configuration? Well, what we do is we get graphene suspended, as we showed before. We ground it electrically, and then we have two two voltages, so two gates. And why do we want two gates? Well, if you set one of these gates to 0, so just traditional experiment, what you see as well, you see a conductor-insulator transition, same as I've seen before. But remember, we can measure the proton permeation through these devices as well. So if you do this, what you see is this is proton current through your crystal, and this is the adsorption. So what you see is most of your protons transmit through the crystal, and only at some point you start to get adsorption. So what this tells you is that proton transmission and adsorption are coupled in this case. Now, if you use a double-gated configuration, what you can do is you can drive as many protons as you want, but you can suppress the adsorption. So basically, you drive protons, suppress absorption. You can do the opposite. So you can suppress proton transmission and now drive proton absorption. What this is telling you is that using this double-gated configuration, you can achieve selectivity between coupled electrochemical processes. And the reason why we can do this is because this gives us a double-gated configuration, allows you to separate the electric field and the charge carrier density in the crystal. So this allows us to map electrochemical processes with independent control of charge carrier density and electric field, which is fundamentally impossible to do in any other way. So this is a map of electronic conductivity in graphene, in charge carrier density versus electric field. And what you see is this conductor-insulator transition. This tells you that has been adsorption in graphene. At the same time, you can measure the proton transmission. And in this case, you see it depends really on electric field. Another thing here is this map also shows that at these high electric fields, proton transport through graphene is accelerated enormously. So everything we had seen before on proton transport is just this purple band here. So we achieve accelerations of orders of magnitude in this configuration. In fact, this transport is so fast that now the system behaves almost as if graphene wasn't there. So at these high electric fields, graphene effectively becomes transparent to proton transport. Why this is relevant? Well, it's relevant beyond proton transport. So if we were to drive these processes using a classical interface, the only available route electrochemical pathway is this narrow green line here. So what we've done here is expand the parameter space in which we can study electrochemical processes. And this is done for just proton transport and absorption. But in principle, you could use this technique to study any electrochemical process that can take place to the crystal. You could study intercalation, water dissociation, oxidation, HR. Any process in principle can be studied this way. This is pathway one of the research lines we're working on. And the second one is, well, we study graphene. This is the strongest material we know, and this was part of the motivation. But that doesn't mean it's necessarily always the best material for all applications. So we decided to investigate which other 2D crystals can present proton permeation. So one of the crystals we decided to investigate is clays and micas. These crystals are abundant soil minerals. And they have an interesting property, which is known as ion exchange. So many of the proton conductors we use, like naphthalene, they're ion exchanges. And this means that if you dunk them in a solution, electrolyte solution, it will soak up the ions from that solution and release the ones inside the material. This process is known as ion exchange, and clays are particularly good at doing this. So if you look at the structure of the clay, it's basically a silicate layer, and in between these layers, you have an exchangeable ion. This ion is usually magnesium, it could be potassium. If you look from the top, what you see is that this forms this nice sort of like hexagonal-ish structure. And at the center of the hexagonal ring, you have this exchangeable ion. So what we did is we wanted to investigate if we could exchange these ions. And what we did is, yes, you can exchange them. If you look at the cross-section, we managed to insert cesium ions into this crystal. If you look from the top, you see this cesium structure here, which tells you that we could exchange successfully with atomic scale this ion exchange process. And the reason why we care about this is because what we can do is, instead of putting cesium ions, we could put protons. So we can do proton exchange. So this is proton conductivity versus 1/T, so a Arrhenius plot of the proton conductivity of mica. What you see is that depends exponentially on temperature. But the key thing here is that these mica layers, this is 2 layers of muscovite, you see that it's pretty proton conductive around 200 Celsius. And why do we care about this? For 2 reasons. First, many hydrogen technologies function better at this temperature range, while at lower temperatures, proton conductors work well, but you need expensive catalysts because the reactions are slow. At very high temperatures, you don't usually need very expensive catalysts, but turning the systems on and off is problematic. So ideally, you want to work within this sweet spot of 200-ish Celsius for these technologies. But unfortunately, there's not many materials that can work in this temperature range. You, of course, have Nafion. All water-based proton conductors are very good, excellent proton conductors, and they work around up to 100 Celsius-ish, roughly. You also have oxides, which are excellent proton conductors as well. They tend to work above 400-ish. So this gap, which is protons materials gap, or sometimes called the Norby gap, it's getting slowly populated, but there's very few materials that can work in this regime. So this is why these new 2D crystals are interesting as a way to fill this gap of materials that are not available. We also investigated other 2D crystals, for example, graphene oxide, which you probably heard is this very interesting material in terms of its properties for water filtration. What we found is that it turns out to be a pretty good proton conductor. We see that it's about 100 times, 50 times better than graphene, and it's also intrinsically permeable. So although you have loads of oxygen groups in the crystal, this crystal remains permeable even in the absence of pinholes in the crystal. Another interesting material is, well, instead of trying to avoid pinholes, put loads of little defects, but they have to be small. So what we did is we put loads of single vacancies in these crystals, and you get something that is called amorphous, or amorphous to the crystal, or amorphous graphene. And what you see is that because these bigger pores, you have much higher proton permeation. We see that now we have proton permeability of the order of 1,000 times higher than graphene, but now you can also start to see permeation of other ions. So graphene is impermeable to all ions except protons, but when you start to introduce these defects, you can see lithium permeation as well. So interesting for other technologies. And with that, well, what this tells you is, well, everything we've studied about proton permeation and permeability in general is really given by a few materials boxed in red, but there's a huge number of crystals. Many of these have not been studied. They're known from their electronic properties, but they haven't studied from a permeation or energy perspective. So there's huge potential to investigate transfer of other ions. You could study hydroxide, lithium ions, oxide ions. So there's huge advantages here. And with that, I'll just leave you with a take-home message, which is 2-dimensional crystals can be intrinsically permeable to protons, and they can allow you, measured in the right conditions, to expand the parameter space at which you can drive several electrochemical processes. And with that, I'll just thank everyone involved, and thank you for your attention.
Any questions that people...
My question is can this be relevant to hydrogen gas generation in some way?
But yeah, I think if you have a material that is proton conductive and impermeable to gases, you could use this to enhance the performance in fuel cells. So you could imagine electrolysis, right? So a problem with these technologies is usually one of the problems they face or challenges is crossover, for example, higher pressures. You could imagine you could use these materials to enhance the performance of some of these technologies.
Yes.
Any other questions? Okay, so thank you very much.
Cheers.
Really appreciate that. Thank you again.